Hi everyone, welcome back to Project 2845. We've made some really excellent progress with the preamp, and we've added in, you can see on the right here, our 6BX7 parallel cathode follower. And then left of the 6BX7 we have our 6AH4 and our 6SN7 preamp tube all the way on the left. So we've got the proposed preamplifier completely prototyped and inside our prototype chassis. For the filaments, what I'm running are now 2 filament transformers. So one of the transformers I purchased last time I'm now using for the 6BX7, and I'm just running this transformer AC to AC, I guess. There's no DC filtering or linear regulator for our 6BX7. And as we discussed, this needs a separate filament winding from our 6AH4 and 6AH7 preamp tubes, which are using this transformer I showed previously, and our linear regulator circuit on that prototype board back there. So with the 6BX7 running AC filaments, the performance is still extremely good, and there's no need, it looks like, to even attempt to run any sort of DC for the 6BX7. And I believe that's mainly because, well, one, it's the last stage, so it's going to be the least sensitive in terms of the preamplifier gain that we're developing and increasing across the preamp. And 2, it is the cathode follower, so this tube itself also develops zero gain. So for those 2 reasons, I think that it doesn't really impact performance running our 6BX7 on AC filaments. The stage performs really well. Here with a 100 millivolt input, we're measuring 1.138 volts output. I am measuring the AP across a new resistive divider on the output of our 6BX7, and I'll show that in a minute. But here's our THD, quite good for this voltage, and it's performing extremely well. If we take a look at our circuit, last time we were looking at our 6SN7 plus 6AH4 stages. Now we've added in the parallel 6BX7 stage and cathode follower that you see here. Like before, I'm using these depletion mode MOSFETs in the constant current source configuration. I've adjusted the resistor values so I can now sync 30 milliamps through our 6BX7 stage. I also added, and I omitted from the schematic and added this in afterwards, a 10 ohm plate resistor so I can measure the current by measuring the voltage developed across this resistor through this stack, and therefore adjust my constant current source appropriately. I have a 1 microfarad output coupling capacitor, which comes into a voltage divider, which I can then measure with my AP, either at the low side or the high side. We need to be careful measuring the high side because if we develop too large of a voltage, we'll violate the AP's maximum AC input voltage spec. So that's why I have the resistive divider here. But this stage works so well, and as we expect, it could care less where the AP is connected in terms of its performance. So even though the AP is a 100 kilo ohm load with 270 picofarads plus whatever cabling capacitance we have, the performance and the gain doesn't change regardless of whether I connect the AP to the output directly here or on the low side of our resistive divider, which is exactly why we want to implement a buffer in the first place. The buffer is much more immune to changes in load impedance across frequency and just changes in load impedance versus its general performance. The voltage divider I've developed here I'm using relatively low resistor values to replicate what I plan to use for my grid leak resistors for the bias of our 845 tubes. So when I add the 845 tubes, when we build the power amp stage, my negative bias voltage will come from here to our 845s, and I'm planning to use somewhere around 47k ohm grid leak resistor for good control and make sure the bias has good control over the grids of our 845s that will be attached over here. So I'm testing this with what I assume will be an approximation of the steady state, or I guess at least low signal swing voltage, assuming the 845s aren't drawing grid current. I'm trying to represent that impedance here by using lower value resistors. And again, the cathode follower doesn't really care within a pretty wide margin the impedance it's driving, and that's the whole point. Here you can see the signal on our oscilloscope. And the one thing that I have noticed, and I guess it's not too unexpected because of the way these cascaded stages now perform, but our headroom is a little bit worse with this cathode follower added compared to just the 6AH4 standalone. So if I increase our signal voltage to 1 volt, you can start to see that the top of our sine wave here is starting to square off. And as we said before, this is the constant current source running out of headroom for our 6AH4 stage. Actually, let me uninvert the polarity. There we go. So this makes more sense now. So this bottom trace here is the input to our 6AH4. This point here, and we can measure here with our oscilloscope because we're isolated from DC because of this blocking capacitor. And then I'm measuring on our oscilloscope right now the entire output, so input, output on our oscilloscope on the low side across this, on the high side of our voltage divider. So my AP and my oscilloscope are connected right there. So this is the 6AH4 input, and this is our 6BX7 cathode follower output. And as we've seen before, as the 6AH4 input goes negative, the plate voltage on the 6AH4 goes higher, and we start running into our constant current source headroom limitation. If I increase to 1.1 volts, you can see we start squaring off pretty high. So this stage with the cathode follower added is not performing quite as well with regards to headroom as it was before. That's not really too unexpected, and the reasoning is, and let me move my schematic out of the way. If we take a look at the grid curves for both our 6AH4 and 6BX7 side by side, what's happening is as our negative input goes this way, our plate voltage on our 6AH4 increases, and we start running into or heading towards where our constant current source headroom limitation is met and our constant current source impedance falls off. On our 6BX7 cathode follower, on our standard plate curves, the cathode voltage actually moves in the opposite direction of the plate voltage. So as our plate voltage would normally increase, our cathode voltage indicated on this new x-axis here, VK, is actually at its minimum 0. So 500 volts on the cathode means we must have 0 volts on the anode of our 6BX7 cathode follower. So in other words, as the signal swing on our 6AH4 moves to the right on the curves, our 6BX7 tube moves on the left. And the opposite is true. If our signal voltage increases on our 6AH4, we move to the left on the 6AH4 curves, but we move to the right on our 6BX7 curves, and now we're running into the constant current source regulations point for that tube. So because of this sort of phase inversion between anode and cathode that we have between these two stages, we're now going to run into our constant current source limitation on both sides of our signal swing. So both negative input signal swings will see this constant current source eating up some headroom, and on positive input signal swings, you'll see this constant current source eating up headroom. I hope that makes sense, but basically, because we now have two constant current sources and we'll run into them with out of phase or opposite signal polarity, we now lose an additional amount of headroom of a constant current source. And as we've said, and as the constant current source testing showed, it's likely around 20 volts or so of headroom. That's fine, but actually, if you look at these curves, that's not what we're seeing. So as I increase the signal or the input voltage, we're clipping only on one side. And in fact, I can keep increasing, so 1.5 input volts. Look how hard we're clipping our constant current source on our 6AH4 stage relative to our 6BX7. You can see the 6BX7 with this input voltage is starting to square off now. Our grid drive actually still looks really linear. What I figured out is going on here is actually grid current effects are shifting the bias, and actually maybe even be able to see this on the oscilloscope if I drop the signal really quickly. Maybe you didn't notice, but this curve shifted up as I reduced my input signal. If we take a look at our schematic again, what's going on is at large input signal swings, we're driving the grid of the 6AH4 near positive or positive voltage, and therefore the grid is now able to pull current and pull grid current. That means we're shifting the bias point of this stage. And we're actually shifting it negative. What that means, if we go back to these curves, as we discussed, our static bias point at increasing signal voltage is actually shifting to the left due to the grid current, and this is known as blocking distortion. So we shift this operating point closer to the left at static sinusoidal input signals. This stage is moving off center, and we're operating closer and closer to the constant current source limitation, and that's why we clip on this side much sooner. With our cathode follower, as we discussed, the exact opposite's happening. I'm actually moving away from its limitation based on the bias point shift of our 6AH4 to the right. So if our bias shifts by a couple volts to the right on our 6AH4, we'll move to a couple volts to the left on our 6BX7. And so we're actually going to continually run into the constant current source limitation on the 6AH4 stage first, well before we'll ever see the constant current source headroom limitation of the 6BX7. So we're clipping asymmetrically, and we'll continue to clip more and more asymmetrically as our signal voltage increases due to the grid current that the 6AH4 tube draws. One way we can prove that what we're seeing is a shift in the bias point causing the stages to move away from their kind of center and maximum peak-to-peak operating point is by just measuring the grid voltage, the DC grid voltage on the input of our 6AH4. So right now I've got our multimeter essentially connected across this 470 k ohm resistor, and as we'd expect, it's hovering around 0 volts. The scale there is actually millivolts, so 10.4 millivolts. This meter has pretty decent AC rejection when it's in the DC voltage setting, which is what we're looking for, because we don't want to measure the AC signal across the cathode resistor. We want to look at the DC, which will tell us what the bias point is doing. So as expected, we're very close to 0 volts. There's a little bit of leakage, which could be maybe some DC leakage from these capacitors. And maybe the grid does draw a little bit of static grid current. But as I increase our signal voltage, what will happen is we'll see the grid voltage start moving negative statically, which means our bias point is shifting more negative. So right now with 100 millivolts input, if I 1 volt RMS, which is close to clipping, look what our bias point did. Our input to the grid has moved negative 1.5 volts nearly, which means we've essentially shifted the static bias point across the cathode from 25 volts to approximately 26.5. We've added negative 1.5 volts of grid bias thus shifting the operating point of this tube. So again, we're just starting to clip. If I move to 1.1 volts, we're now clipping quite heavily, 3.687 volts. So we're continuing to shift, as we discussed, our operating point more and more towards negative grid bias because of the AC signal swing causing grid current and therefore shifting the static bias point. I can also prove this another way. If I back down the signal for a second, the AP has the ability to do some burst testing. So if I go to burst normal, what I can do is I can set a number of high duty cycle or high peak to peak amplitude cycles relative to low amplitude cycles. So right now, turn up the brightness on the oscilloscope a little bit. If I zoom way out, I'm doing 1 high amplitude signal to 10 low amplitude cycles. And that pattern just continues to repeat with the AP. What I'm going to do, we're zooming in on the high amplitude cycle right now. I'm going to increase our signal voltage to 1 volt. Look where we're clipping. We're clipping on the opposite side. This is the cathode follower's constant current source starting to give us a little bit of squaring off. The 6H4 is fine. We haven't accumulated enough AC cycles to statically shift the bias point of the stage yet. We're close to being centered up quite well. So let me make this a little more dramatic and go to 1.1 volt RMS input. There you can see now. Now we're squared off. Shifted the bias point slightly because this is now squarer than this, but we're still roughly centered. What's interesting is as I add more cycles, we can actually continue to see the bias point shifting, and what we'll see is the low side, our 6px7 constant current source regulation point, go away, and this will start to round off, and this side will clip harder. And that's because we're accumulating more cycles to shift our bias point due to the time constants of the R and C here. And what's essentially happening, this is known as blocking distortion, but what's happening is we're shifting the charge across this capacitor because of the grid current in one direction, but on negative signal swings we can only pull current back to recharge this capacitor across a much larger impedance, 470K. So the impedance imbalance of current flow due to grid current only occurring in one direction causes this point to go negative, which is what we are seeing on our multimeter. So if we go back to the oscilloscope, I'm going to add cycles. So here's 2, 3, 4, 5. Might have been hard to see, but notice how the bottom is cleaning up and the top is squaring off even more. Because this tube will always draw grid current first, because of this capacitor and the time constants associated with the shifting bias point, the best solution is actually just going to be to increase our voltage rails and give these stages more headroom and shift our bias point on our 6AH4, shift its static bias point more to the left so we never draw grid current with a positive input signal, or reduce the amount of grid current we draw. So more voltage headroom will extend this range out here and will recenter our 6AH4. And that's probably going to be the best solution to get back to very close to our headroom that we needed before. I'll mention, I've already looked at what the headroom on the stage actually is. And we're about 180 volts peak. I'd like to get this closer to our 400 volts peak to peak, or 200 volt peak that we had before, which will give us plenty of margin for our 845 operating point. So I'd like to maintain that margin, which is my goal with adjusting the bias. Before we close, what I will show is the THD versus output profile. So let me reduce the signal a little bit to something a little bit better. Fumbling with the mouse a little bit. Here's our THD at this operating point. I'll quickly run the THD versus output signal profile of the stage at 1 kilohertz, just to show how it does perform. And it performs extremely well, it really does. And like I said, with that buffer, it could care less if we connect the AP directly to the output of the buffer or across our resistor divider. And I'll do some future testing too to measure the output impedance of the buffer to see what it actually is. So we can see here our clipping point is around 11 volts. With our new, and I'm across the voltage divider right now, so 11 times square root of 2 to get peak, multiplied by 11.47. 11.47 is our voltage divider ratio that I've got installed right now. 178 volts peak. So that's roughly about this point here. I'd like to try to kick this out just a little bit more and give us a little bit more headroom. The other thing I'll note here is, and I'll compare this back at the computer probably in a future video where I do all my analysis on this stage, and I'll run bandwidth, noise, and just run a full gamut of tests. But off the bat, I can see that this THD profile is a little bit better than when we ran just our 6H4 alone without the 6BX7. And the reason is we don't have the THD or distortion cancellation effects, or sorry, we do now have THD and distortion cancellation effects in play because of these two stages operating out of phase. So the curves, the plate curves that give us some compression R6H4 are uncompressed essentially by the 6BX7 operating out of phase. And that's what I mean by distortion cancellation. So that effect is at play here, giving us slightly better performance than what we measured with our 6H4 alone. Anyway, I hope this was useful for everyone and interesting. If there's anything else I can think of while I've got this on the bench today, I'll add it to the video. But what I plan to do is change the operating point, and maybe I'll document that, get a little bit more headroom out of these stages, kind of get everything locked down in terms of component values, and then I'll run a full gamut of tests, and I'll look at bandwidth too with the AP connected directly here. So that's my plan, and thanks for watching. Take care.